Good morning, everybody. Thank you for being here. My name is John Rask. I'm the Director of Astrobiology Operations here at NASA Ames, and welcome you to this Astrobiology Science Forum. It's a very auspicious day today. There's a historic in many regards, and it was about almost 20 years ago to the day that I was a graduate student that was attending the very first Astrobiology Science Conference here. And it's amazing to see how the community and the science have developed over the years. And it's my privilege and honor to be here today and share in the excitement of the success of the NEI and the future of astrobiology at Ames and at NASA in general. And so with that, I would like to introduce David Kooris Meyer, our Associate Center Director for Research and Technology, to kick things off and introduce our keynote speaker. David. Thank you.
Good morning, and damp the applause. Seriously, thank you all for coming today. This is really a great opportunity. I think today is actually a great representation of what NASA Ames is. NASA Ames is actually turning 80 years old. We are 80 years old this December. Officially, we're 20 years older than NASA corporate is, because we were part of the original NASA National Advisory Committee on Aeronautics. Founded in 1939 here at Moffett Field. And we were set up as a research center. And we have stayed true to that character as a research center. So when we started, we were only really doing aeronautics, and we came up with the idea of the swept back wing. And then we got into looking at how to slow things down in the atmosphere, and we came up with the blunt body to slow things down and compress the flow. And then we got into NASA when NASA was formed soon after Sputnik. And we took over the life science activities and the Pioneer missions for the agency, doing the first outer planet exploration activities in Pioneer Venus. And then we got into high-end computing and proved that we could actually do full-scale computational modeling of fluid dynamics. And then we got into human factors and AI and robotics, and that's when I came into the fore. And then we got into this area where we knew there was a field that NASA needed to do, that NASA needed to aggregate a whole bunch of disparate, independent studies that had been going on what it means to be alive, what life is, what life characteristics are. There was a term of art at the time called exobiology, and we didn't think that was quite good enough. And we came up with something else called astrobiology and proposed it and got NASA corporate to buy in on it, and ended up establishing for NASA and hosting the NASA Astrobiology Institute. And that is just a perfect model of what I view NASA Ames to be. We are a research institution, and we are deeply proud of that history, that heritage, and that future. We start new things, we get them up, we get them running, we validate, and we basically integrate with the community. And then we continue on. And Astrobiology Institute and the whole field of astrobiology, I think, is an example of how well Ames has worked to make that happen. This is kind of, I've said this before to headquarters and to our local people, I view this more as a graduation. You know, NAI has graduated. They've achieved it. We've passed through high school. Actually, we're well into our graduate studies. And we've now got a vibrant community out there. There's astrobiology expertise and activities going on at multiple NASA centers, at multiple academic institutions all around the world. We've had over almost $1 billion go through the NASA Astrobiology Institute. This is just a phenomenal thing. We have people like John shared who never knew anything but the Astrobiology Institute and astrobiology occurring at NASA. We have now real, and I don't mean to diminish Viking or anything like that, but we have current, vibrant, real missions on the books that are going after life detection. We have Ames and Goddard and JPL and APL and others all engaged in common missions going after life detection and life detection instrumentation. There is wonderful stuff that's going to happen in the next 20 years. So this is just a phenomenal opportunity for us to recognize the origin, the distribution, the evolution and the future of what astrobiology can and should be, both at NASA Ames, at NASA corporate, and around the world in the research community. This is just a wonderful, truly wonderful opportunity. As I said, I'm very proud that Ames is a research center. Just to give you an idea of some of the chaos that I'm also proud of that's going on at Ames today is we've got across the field a whole other large community of people talking on convergent aerospace solutions for unmanned aerial vehicles in the airspace. That's been going on for 2 days. We have this minor event, which you may or may not have heard about, where we have the NASA administrator and the vice president here talking lunar surface return on our Viper rover and flying in the vertical motion simulator, a simulator of the lunar lander system. Again, this speaks to NASA, its breadth corporately and otherwise in research and technology development for the betterment of humankind and the exploration of space and aerospace activities, and to NASA Ames' role in being on literally sometimes the bleeding, and mean bleeding to the point it hurts occasionally, of what it means to be doing the research and technology development. So again, I thank you so much for coming. I apologize in advance that I'm gonna get up and leave to go handle some other things during the middle of the day. You know, this whole vice presidential thing, where we'll have to deal with that a little bit, but I will be back, and Eugene plans to come back, and we've actually informed the administrator who is here today, and he's expressed some interest. His time will be highly constrained, but in potentially even swinging by towards the end of the day, which we're very pleased to get his support on that, because we believe this is still a very vibrant and growing field, and now in somewhat it's out of its chrysalis, or it's flowered. Pick your analogy. With that, I want to introduce the ninth former, well, not, I shouldn't say it that way, the ninth center director for NASA Ames, a former center director, not to diminish Eugene's role at this point now, Mr. Scott Hubbard. Professor Hubbard is currently at Stanford University in the Aero and Astronautics department. Thank you, Scott. And I've known Scott for a long time. When he first, I recognized, this gentleman when I was simply a grunt researcher. He was managing our first return to the moon in a long time, the Lunar Prospector mission that was managed out of here under Scott's tutelage. And then he got dragged into this whole first Mars-R activity, where really after several failures, unfortunate in the Mars program, Scott was brought in to look at this corporately for NASA. How can we shake this up? What should we do? And I think it was under his banner that they came up with the whole follow the water. And that has made an incredibly successful heritage of NASA Mars missions. In addition to that, then Scott came on board as the NASA Center Director here at Ames Research Center, and almost immediately got dragged into a very unfortunate event, but very important representational role as the only NASA member on the Columbia Accident Investigation Board, and was instrumental in determining the actual cause of that terrible tragedy and failure. Under Scott's purview, the Astrobiology Institute took off and flourished, and has done so well. And we're so pleased to have members of the current CANs and past CANs and RCNs and the astrobiology research teams, both here at NASA, Ames, Goddard, JPL, and around the agency, and all the other international partners and academic partners listening in today. We thank you so much for coming. I'd like to introduce our first speaker, Professor Scott Harper.
Well, I'm glad to be here today, be able to visit with a number of old friends. And let me say happy 20th anniversary to the Astrobiology Institute. Happy 25th anniversary to the field of astrobiology, and maybe happy 60th anniversary to exobiology. So what we want to do is, can we bring up the agenda quickly? Is that possible? I just want to go through briefly what we're going to do in the first session this morning. I'm the chair. and we're going to look back at the origins of astrobiology. And that means a couple of things. I'm going to set the stage with some of the science, and in particular, how the Astrobiology Institute got formed. We're going to hear from John Rummel about exobiology, which was a forerunner going back 60 years. And then we're going to have the tag team of Dave and Dave over here talk about the science, the first astrobiology conference, incorporating some incredible interest from the broader scientific community, and then how the road mapping that was so critical to the early astrobiology program and institute came about. Lynn Harper then is going to tell us a little bit about why would Nobel laureates be interested in this field. That's going to be, I think, a fascinating insight. Rose Grimes there she is. Talk about the early years of the institute, and then we've got a segment from Carl Pilcher, who was, I think, the third or fourth maybe director of depends on how you count, yeah, of that. So with that in mind, let's switch over to the presentation that I put together that has to do with foundations of both the science, and be sure you get final there, because there was a last minute change in the program, and so I made a few modifications. There we go. Perfect. Okay. Let me just make one comment. In researching this, to be sure that I had my timeline and my facts straight and so forth, I went back into a lot of old documents that I still had. I've donated the bulk of my life's work to the archive at Stanford. I would have liked to have had it here, but it included things from Lawrence Berkeley Laboratory and Stanford, and so it's over there if anybody wants to look at it. And in my searches, I came up with an Excel spreadsheet of Senior Executive Service Candidate Development Program people, and there was a Meyer on there, and there was a 2 on there. And I'm so glad to see that planning 15 years ago worked out as well as it did. So Dave, Eugene, and the whole staff are doing a terrific job. I pulled together this talk from 3 pieces of things that I wrote or co-authored, one for the NASA 50th anniversary, and then 2 talks at the International Astronautical Congress. So that's where the material originated from. And in addition to the title that's in the program about founding the Institute, I added a subtext, and I hope to show you in the next 25 minutes or so that it was a convergence of several things. It was the compelling science. It was also the politics of the era, the technology that was emerging, and how programs were put together. And I think it's quite an interesting story, some of which you may not have heard before. Alrighty. So why am I here? What do I plan to cover? In my career at NASA, I had 3 roles that were relevant to astrobiology and the Institute. I think I was an original member of the group, many of whom are here, that saw astrobiology as the science of the future for NASA and the best way to define the expertise that we have and had here at Ames. And this included being part, along with at least one of these, my friend Dave Morrison, various studies like the Science Institute team and the Federal Lab Review and so forth. You're going to hear from these key individuals later in the conference about the roadmaps and the history and so forth. And then I was named the interim director, which sounds sort of like a placeholder or a station keeper, but actually my charter, which came from Dan Goldin. He gave the same charter to about 5 different people, but I ended up with it and was sort of founding the Institute with creating the various mechanisms for how you pull together all of this science on a virtual basis. And then together with some others, Lynn, a few other people who are probably not in the room, we went out and recruited what Dan Goldin told us to do, which was to find the King Kong biologist who was going to help put this on the map. Now, from 25 years ago or so, I think that it's still true, the observation that occurred to me and others then, that to make astrobiology and the Institute a success, you needed three things. Of course, the novel science, collaborating in a multidisciplinary way to address these big questions. Are we alone? How did life form? And so forth. We had to have, second, an organizational structure to facilitate that. It was not the sort of thing that at the time, and I think it's still true, that you can make happen simply with a grant mechanism. And then we need visibility and validation. And that's where getting Barry Bloomberg to be the first permanent director came in, and where all of the outreach that many of you know about and have participated in helped to make this a worldwide phenomenon. So let's go back a little bit more that Dave Korsmeyer talked about. We were founded here in December of 1939. It was Ames Aeronautical Laboratory. Did some tremendous work with the early wind tunnels. And then when the Space Act was passed and we were incorporated into NASA's Ames Research Center, we got two space assignments: space physics, that was the Pioneer series, and then space life sciences. Not only things like biosatellite and the ground laboratories, but leading to literally hundreds of payloads aboard the shuttle and Skylab and early life science experiments. Very quickly after the founding of NASA Ames, or founding of NASA and Ames as Ames Research Center, and getting that life science assignment, Chuck Klein, I never did understand how Harold became Chuck, but you know, but I knew him as Chuck, tremendous scientist, very innovative, and early on expressed the interest that was growing out of certain elements of the scientific field, like the Harold Urey experiment and other places, saying, you know, we need to understand whether life could have formed elsewhere, and helped to develop the field of exobiology beginning in '59. And John Rummel's going to talk about that in a few minutes. So fast forward 35 years to the mid-90s, and it was a perfect storm of science. Everything from the Mars rock, which led to a whole new Mars program once we got past the initial failures that where I wish Dan was here. You know, he put his arm around me and said, "Son, your country needs you. You have to come to Washington and fix the mess." But the scientific underpinnings of this was the discovery of this Mars meteorite, which a group, through their 4 lines of investigation, said they believed contained remnants of early life on Mars. There was the data from Europa showing this moon of Jupiter with a thick ice shell and a putative ocean underneath. The first detection of an extrasolar planet, which, as everybody here probably knows, just won the Nobel Prize in physics. The Human Genome Project was moving along quickly. So this confluence of science gave rise to the idea that we could really study and make progress in understanding things like how did life emerge, and did it emerge elsewhere, and are we alone in the universe? But that's not all that was going on, particularly from an Ames perspective. It was a perfect storm in politics and programs as well. So some of you may recall that there was a historic vote in June of '93 that saved the International Space Station by 1 vote, and that consumed Dan Goldin's complete attention. Once that was passed, Dan and his deputy, actually associate deputy administrator, Jack Daly, started looking at the entire structure of NASA, the roles, the missions, the organization, and a whole bunch of initiatives got set loose by various names. One, called the Zero Base Review, suggested that Ames might transfer its scientific capability to an institute. Wes Huntress, who was out here on a famous Sunday afternoon, said, you know, we probably ought to call this field, it's not we've got cosmochemistry is taken, and cosmobiology, how about astrobiology? Now, it turns out with research that term had been used before, but Wes was the one, the associate administrator for science at the time, for space, who said, let's call this collection of things that you have developed at Ames astrobiology. And then in March of 95, all this was happening at the same time. The science was emerging and people were looking at the structure of the agency. Franz Cordova, the chief scientist, wrote a letter in support of the idea of a science institute. So then, barely 2 months later, Dan Goldin announced that Ames was the lead center for astrobiology. Major accomplishment, first designation of a new field of inquiry based on this emerging science. And this was what a group of us who worked on this, I'm looking at Dave Morrison, Dave DeMarais, Lynn Harper, all the other folks out there, said was astrobiology. It was taking an existing program, exobiology. It was taking evolutionary biology. It was combining scientific interests from space science, life science, and earth science into a new way of looking at questions of life in the universe. And this is what Goldin embraced and what the science community was beginning to resonate with. And as you'll hear later from Dave and Dave, part of the initial roadmaps and studies. But there was the Science Institute team running in the background, and they issued a report, the final report in February of '96, that said, well, there's 11 institutes that have been proposed by the zero-based review, and they're in various stages of readiness, but only 3 are ready to go right now. One of those is the Astrobiology Institute and Ames, and so NASA should proceed immediately to, I'm jumping to the bottom sub-bullet, pursue legislative authorities required and recommended prior to moving ahead with astrobiology and the microgravity institutes. These new legislative authorities contemplated moving hundreds of civil servants from their current badge assignment to a non-governmental institute. So this would have been an extraordinary shift in the way things were working here at NASA Ames. It would have meant that the total civil service complement could have been as low as 300, with the bulk of the scientists and a lot of the support work moving to a non-governmental entity. Very interesting counterpoint to the scientific excitement, and caused a lot of study, angst, and introspection and discussion at the time. However, once this search for legislative authority reached the Office of Government Ethics, they said, no way. There are criminal laws on the books having to do with post-employment restrictions. You just can't pick your badge that says civil servant, astrobiologist one day, and flip it around and become astrobiologist working for the Institute the next day. That's just not possible. So based on the pushback from the administration at the time and from Capitol Hill Congress at the time, Jack Daly sent out a letter advising us at Ames to proceed with the Institute, but not move any civil servants. Now, at that point, Dave Morrison just showed me a very interesting letter from the same period, early '97, where Dan Goldin was berating people for not making progress, and wanted Dave Morrison and others to, I think Jerry Soffin at Goddard, to help with the Institute. But Dan was famous for giving the same assignment to multiple people in hopes that something would happen, I suppose. So I had an interview with Dan. He decided at that point that he was Hyman Rickover. And Rickover was famous for interviewing every person who was about to move into flag rank. If that person was about to become an admiral of some sort, rear admiral, 1 star, He would interview them personally. So for a while, Dan interviewed every person who was about to be nominated into the senior executive service. So I had an interview in 97 with Dan, and he told me, and this is a near quote, best I can remember, "I want you to create an astrobiology institute, but I'm not going to give you a nickel for bricks and mortar." And I said, okay, I'll see what I can do. By the summer of that year, Wes Hunter's had formally assigned the institute responsibility to Ames. And so between the period of summer of 97 to fall of 97, there was this intensive effort to create what became the first cooperative agreement notice that would establish a new research program. So here was all the challenges that we had to face early on. How do you create a scientific institute devoted to a new interdisciplinary, multidisciplinary, the words tend to be used interchangeably, although some prefer one over the other, called astrobiology? How do we get physicists and astronomers and biologists and chemists to speak each other's language? You know, how do you get parsecs from one group talking to another group that's dealing in nanometers? And that was, we felt, one of the very first challenges, and the road mapping exercise helped a lot with that. And then how do we incentivize or even require cross-discipline collaboration when these groups are geographically dispersed? You have to deal with big questions across departments, schools, institutions, which maybe don't talk to each other. In fact, there was a study when they built a building at UC Santa Cruz that said if you're more than 10 doors away from your colleague, even if you're in the same field, you will never talk to them. That proximity was a key factor in introducing collaboration. So how are we going to do that, yet at the same time not spend a nickel on bricks and mortar? Well, one answer that drew on another part of Ames was to take advantage of the high-speed revolution that Dave Korsmeyer mentioned a minute ago, the next generation internet, the collaboration hardware and software. So we had to think about that, but be aware of human nature and the fact that people tend to gravitate to their tribe, their silo, their stovepipe. And part of that, as you'll see in a minute, was that we realized it's hard to have a virtual relationship with someone who you have not met face-to-face. So having an early face-to-face get-together and an exchange of scientific ideas was critical to implementing the virtual communications that occurred later. And then finally, we had to have a function that integrated all this at Ames that could solicit research, invest in new technology, think about future directions, coordinate education and outreach, but without adding significant overhead to the total enterprise or undermining a PI's scientific freedom of what they had proposed in their application to the cooperative agreement. So we took 5% as a target figure for the overhead and said, you know, in writing the position description for the director, it needed to provide leadership on one hand, but maintain a light touch with respect to the principal investigators on the other hand. Not an easy thing to do. Well, what were the answers? There are three of them. Excuse me. First of all, the first cooperative agreement notice. And I put Michael Meyer's picture up here because he and I worked a great deal together to solve the problem of how you incentivize and require this type of interdisciplinary research and so forth. Couldn't be a contract. That's far too restrictive. A grant is fundamentally a gift. So the cooperative agreement where all the institutions were making contributions turned out to be the right answer. But in the introduction to this, and thanks to Dave DeMarais who dug up the original one, it's hard to find, I found the introduction where I wrote that this was an experiment that we expected to evolve. We knew that it was not necessarily going to work out the same way that we started, and that there would need to be adjustments. So rather than soliciting for a single entity, the way NASA did with the Lunar and Planetary Institute for conferences and workshops and so forth. We asked for multiple PI-led groups to propose, but they had to show that they were working across not only departmental lines, their group lines, but maybe even various institutions, schools, and so forth. That the science themes were drawn from the road mapping, that the education and outreach, while it would be integrated, was very significant for each group, and that they had to show that their contributions would be significant from their institution. That's part of what a cooperative agreement is. And that they would be actually and actively engaged in a virtual organization. So this was quite a bit different than the other cooperative agreements. It was breaking new ground in a number of different directions. And along the way, of course, of getting ready to put this out, we had to go find the money. And the three organizations we were dealing with had shall we say, various degrees of willingness to put the funding on the table. But in the end, we got about $10 million together for the first year. The other answers were the structure and the technology. Now, the structure had to do with an implementation plan that I was largely responsible for writing. It was something like a project plan as applied to multidisciplinary science, and a way of making sure everybody knew what they were responsible for while integrating the comments of the three different headquarters funding agencies or funding organizations, and outlining the relationship between the original 11 nodes and that represented about 300 people. The second piece, the technology, was the video conferencing, the contributions of intelligent systems and high performance computing here at Ames, and using this, deploying these tools and beginning to use them to encourage and grow and facilitate the virtual collaboration that was necessary to get across all of these institutional lines and all of the geographic dispersion. So that led to the first institute-wide meeting being in November of '98. Final piece, remember I said there are three pieces. One's the compelling science, two is the new organizational structure, and three is visibility and validation. So we needed to find, as you'll see in a minute, someone to help us put this on the map. Scientifically, the person had to be willing to embrace the challenge of establishing a new science, had to be at a point in his or her career where they were willing to take such a risk. Clearly, it couldn't be someone that was still up for tenure, maybe not even mid-career, because that's where you're establishing even more of your credibility. And to have enough scientific wheelbase, enough breadth to be able to go from physics to astronomy to chemistry to biology, and to accomplish what needed to be done. There are also programmatic and legal constraints. So you have to be able to be here. Having a virtual director doesn't mean that you're going to get the job done. You have to be able to work with the levers of control for integrating the institute. And then sufficiently free of conflicts of interest that you passed not only the legal review, but the sniff test, the appearances of whether or not your home institution might be one where you were self-dealing and sending money to them in an inappropriate way. So when I met with Dan in September of '98, he had this famous quote that I've used many times: "I want a King Kong biologist who will put astrobiology and the Institute on the map." We put a search committee together at the same time. It was chaired by France Cordova, but there were no immediate results. Well, enter Mal Cohen. Mel said, "Well, my brother Stanley over at Stanford, he's working with this visiting scientist who might be interested in pursuing these goals." And so that led to the first permanent director, Barry Bloomberg, appointed May 15th, 1999. I know we're going to have a lot more words about Barry, so I will leave that to later parts of the program. And just note that the culmination of these several years worth of work was the establishment of a virtual institute, 11 nodes, 11 PI-led organizations, about 10 million spent on that. And we got our first grants, first cooperative agreements awarded in May of '98. So I will just conclude by saying pretty much what I started with, that I think astrobiology is the scientific heart of space exploration. It was begun as a discipline, you could argue, in '95. It deals with these fundamental questions. It seeks to establish what habitable environments are, biosignatures. But the question of are we alone, the one that astrobiology embraces, is, I think, not only the past key to scientific exploration by NASA, but the future key as well. Thank you very much. So I think we're pretty much right on time, and we're ready to bring up the Dave Morrison and Dave DeMarais discussion of, no, I'm sorry, you're going to play the John Rummel piece. Very good. Thank you.
In 1985, I ended up leaving Stanford and going to NASA Ames to be a postdoc in controlled ecological life support systems. But I found myself immersed in a large group of exobiologists and picked up a little bit. Even half of my postdoctoral advisor was in exobiology. So I started to pick it up by osmosis. And I learned, among other things, how Joshua Lederberg had defined the field, looking for a broader perspective on biology. There are a number of ways that Ames was interested in doing that. At the time I got to Ames, we were getting rid of spark discharge chambers and that sort of work, and moving into more molecular and computational methods. One of the first things I ended up doing is cleaning out a laboratory and putting in the vacs. Eventually I was systems manager on that. That was fun. NASA exobiology goals from 1973 are search for life, search for precursors or evidence of past life, and control and inventory spacecraft contamination. Little did I know that I was going to end up doing a whole lot more of that. In 1986, the ISL meeting was coming to town, and the folks at Ames put together this really nice mural along with a local artist, and provided for a place for all of the cosmic origin of the biogenic elements and compounds from the Big Bang to the Big Brain would go on. Eventually, it was modified by the local management to ensure that whatever happened out in the cosmos ended up in evolution of what was the highest form of life at NASA exobiology at the time, which was the search for extraterrestrial intelligence on that mountaintop on the far right. In 1986, I got to know some of the principal investigators for the program. Only one of them asked me to dance, and it was a privilege and a pleasure to meet Lynn Margulis and to be able to have her as a friend all the way through my management of the program. We had a variety of really classic people in the program at the time: Carl Sagan, Juana Rowe. We had Leslie Orgel, Stanley Miller, Jill Tarter, and Carl Woza. Some really excellent people. Some were better known than others. Here's Carl Sagan as a kid, suggesting that there might be hundreds of stars out there. He became better known for billions later on. But some of the new exobiology investigators that started out the program were there to fix up whatever they could about our understanding of how we came to be and where we might be going. Between Chris Chiba, Jerry Joyce, Lynn Rothschild, and one of them, Jack Szostak, ended up with the Nobel Prize for work he'd done elsewhere. The habitation of the NASA Life Sciences Division was under question at the time, but this is the group of people who all suffered through NASA headquarters at the time. Freeman Quimby had passed away, but in 1993, Dick Young, Don DeVincenzi, Mike Meyer, and I got to get our picture taken together in Barcelona. And Michael New and Carl Pilcher came on after that. Early on, exobiology had made a major investment in Mars exploration, and some of that had paid off. Some of it was a little quizzical based on what we know about biology now, but one of the fun things about this image here from Jet Propulsion Laboratory is that the quality assurance guy has hairier arms than anybody else in the picture, and nobody's wearing a face mask. That's okay. That went for 118 degrees Celsius for 100 hours. So at least they didn't take anything with them that grew in the life detection experiments at the time. We learned that water on Mars was something we don't really understand very well, and water complex with ultraviolet radiation and Mars mineralogy is something we still don't understand. But it was a good place to start with the Viking missions. Unfortunately, the Viking life detection results have been problematic for decades in that we don't really understand what happened there. And we're not sure exactly if we can afford to do it again, but I hope we will. And I hope we'll have results that are a lot easier to vote on than the ones in 1976, 77. All right. Well, we did learn a lot about life on Earth. And Tom Brock and others had invested lots of time and energy in looking at places like Yellowstone National Park, understanding the origin and the capabilities of microbial species there. We had people like Imre Friedman, who in the Beacon Sandstone of Antarctica found a nice happy place for algae, lichens, and fungi and bacteria to live inside of the rocks, as if the rocks were a nice little greenhouse for them. And everything in between was possible. Carl Woese's relatedness capabilities and the whole new branch of life called the archaea were detections that happened because of the exobiology program and a lot of the scientific insights of Dick Young. I have to give him great credit for that, and I've written about that elsewhere. Organic compounds on the early Earth could be brought in by a number of ways, whether it's through atmospheric processes in the middle, meteorites falling from the sky, or from deep sea hydrothermal vent processes. In fact, one of the funny things about Viking is that we didn't discover deep sea hydrothermal vents and the profusion of life that we find here on Earth until 7 months after Viking first landed on Mars. And at that time, the only person anywhere close to being a biologist on board that ship was a journalist. So it was an interesting place to be at the time. We find out that what comes from the sky can hurt you. And whether it's the Chicxulub meteorite or whether it's another asteroid, in this case, Manicouagan in Canada, that's the Alvarez group in the upper right. And looking at iridium anomalies throughout the Earth tells you that global effects can come from things that you don't detect, and it might sneak up on you in the dark. NASA Exobiology program published a series of reports that encapsulated the scientific opportunities at the time and pointed a way towards flight experiments and other kinds of experiments that could be done to advance the science of exobiology. They were joined by the Space Studies Board recommendations to NASA on the search for life's origins, and NASA's exobiology goals at the time were to look at understand the origin, evolution, and distribution of life in the universe, and look at the pathways taken by the biogenic elements from the origin of the universe through major epochs into the evolution of living systems and their precursors. This was particularly interesting, and we split the program up in a particular way, but we also realized that this view of exobiology required a certain amount of capability to be put into place to look at some things on a larger scale. I was proud that the Life Sciences Division put together a NASA Specialized Center of Research and Training in the origin of life at University of California, San Diego, with Stanley Miller as the principal investigator. And later on, we had an extension ENSCORT on the East Coast at Rensselaer Polytechnic. This was a significant investment for NASA research and brought along a number of excellent students along the way. In the past, of course, we had been intrigued by what we've seen around Jupiter with the Galilean satellites. And we thought that there might be interesting things to find out there. And theoretically, we realized that Europa could have an ocean. We were concerned about cloud creatures only for a little while, and these played a role in giving Galileo to a planetary protection strain. But effectively, what we turned out is that the ocean on Europa, not balloon creatures, was the most important part of what we needed to protect to enjoy the search for life in the Galilean satellites. Elsewhere, is there life out there? Are we alone, or do we already own everything? Do the numbers. We can see great opportunity for billions and billions of planets around solar-type stars in the universe, and a fair number of those that are detectable potentially from right here. So SETI, the search for extraterrestrial intelligence, the search for extraterrestrial technology, is exobiology with astronomical tools. And we were able to get the SETI microwave observing project started, unfortunately at a premature demise within NASA, but went on to do other things. Just after I left the exobiology program, Mike Meyer and company fielded this report, which has been extremely influential and spelled out the NASA Mars exploration strategy for several decades. And hopefully we will be able to get to the finer points of that and find life. The world changed when ALH 84001 came forward, some of which the research was sponsored by exobiology program. And it's been a great story in the past, and continues to be a great story for the future. I'd like to thank you for your attention, and thank Mel Avener, Lynn Harper, and Bob McElroy for the opportunities I got working at NASA. Thank you.
That was a wonderful historical retrospective on exobiology. Wonderful historical perspective on exobiology and how it led up to where we are today. I have added up the number of minutes of content, and it's 105, and I've looked at the schedule allocation, and it's 105. So we don't, unfortunately, really have time for questions. But what I will suggest is when we get to the break, that the people who have been speaking will be around here having a cup of coffee. And if you've got questions, if you want to pursue one of the comments or presentations a little further, we'll all be glad to talk to you. So now what we want to do is to have the next 30 minutes of discussion about the early science and conference that on astrobiology, followed by a much more detailed examination of the astrobiology road mapping. So to begin this, let me introduce my longtime friend and colleague, Dave Morrison. Dave?
Thanks, Scott. It's great to see you and all the people here, old friends, memories of the past, and it will be interesting to put together all of the things people have said. Among the people who made astrobiology, and particularly the Astrobiology Institute, possible was Dan Goldin, who helped plan this program but isn't here. And I just want to acknowledge him and two of his two amigos that made an interesting combination, and that is Ray Bloomberg, Carl Sagan, and Dan Goldin. Of those, Dan Goldin was not the nicest of the persons. And I just found in my files a note he sent to me in 1997, which is sort of typical Dan Goldin. I told Harry McDonald, who was the director of Ames, and Dave Morrison to establish an Astrobiology Institute, and we're looking to them for leadership in this important field. I want to beat up on you, We still don't know how to identify life on any planet in another solar system. You have got to work on this. The Astrobiology Institute should be working on this. I want to see some progress. I am not happy with the Origins plans for detection of planets around other stars. We do not need one big expensive mission. We don't need a huge trust. I'm not a happy camper. I want you to work on smaller incremental approaches. I know about Kepler. Morrison has argued with me. Yes, it's true. Argued with me several times about it. I'm not the one to convince. You must convince your scientific colleagues and get Kepler past peer review. You guys at Ames have to take leadership in astrobiology, the intellectual leadership on Origins. We need the best brains in the country working on this. I expect Ames to provide the requirements for the missions that JPL will implement. I want Ames to have the best biologists. You need to hire more people, the top people. Is your center director letting you hire more people? If he doesn't give you the slots, let me know. What do you mean the headquarters Life Sciences is not enthusiastic about supporting the Astrobiology Institute? They better support it. I'm going to go kick Arnold Nicogossian in the shins and make sure he does. This is a typical missive from Dan Goldin. Now, to get more serious, the plans for what astrobiology would be we've been talked about in general terms. But when you got down to the specifics, it's difficult because it is so cross-disciplinary. And it did not conform to the way disciplines are organized in universities, for instance. So here we were wanting to put out cooperative agreement notices and get universities or other research organizations with top people to want to join the Institute. That is not the way they thought. They may have thought an institute was a great idea as long as they ran it, and not something that would be controlled by the government. There are many fine research institutes, even here in the Bay Area, wonderful ones, but they have their own directors, their own staffs, their own sources of money, often with large amounts from universities like Stanford. And their first reaction when we approached them about joining an institute was, oh, that's great. We have good things we can do, and we like astrobiology. But then they say, and we can run it. We can do the institute. We have sources of funds. We have high prestige faculty. And so we'll be glad to do it. We'll start with $15 million for a building. We'll need another $10 million to hire new faculty, and we'll run it, which probably would have worked. But it wasn't what NASA had in mind, and NASA Ames certainly didn't have an extra 25 or 30 million to put into bricks and mortars. And this is what drove us to one of the most distinguishing parts of the Astrobiology Institute, that it is a virtual institute. It is not a bricks and mortar institute. And it's an institute that doesn't just create a scientific organization, but tries to take the best of already existing organizations and to bring together in this virtual mode, which hadn't really been tried much before, a system in which lots of different people, different attitudes, with their students, with their laboratories, could work together. And that just isn't the usual way academic universities work. And that has always been a question for the Institute. How much independence does each group have? How much do they do what we at NASA always had as an objective? Pick the best people in different institutions and create a situation in which they can collaborate and work together. An example of how new this was a time I went down to UC Santa Barbara to meet with some of their faculty. This is when people were preparing to propose for the Institute. And talk about what astrobiology was. You may have gotten the impression from Scott that astrobiology was already a popular idea, but not really so. I had a group of about 20, 25 of the faculty that were brought together to hear my overview of astrobiology in the Institute. And the most interesting thing was that we spent the first half hour of the people who had come, the professors who had come, introducing themselves to each other, because there were astronomers, there were earth scientists, atmospheric scientists, biologists, and they literally did not know each other, let alone know each other's research abilities. And we've had that all along. We've had terrific universities or universe group scientists that would like to be part of astrobiology, but only if they can run it, and not with this sort of outreach to be truly multidisciplinary. Well, what astrobiology tried to do from the beginning, before the Institute was even formed, what we at Ames tried to do was to bring together interested scientists and have road mapping sessions, planning sessions, to try to determine what the appropriate mix might be, understanding that we couldn't dictate from the top exactly what we were going to do. We wanted to pull it up from the grassroots, from top scientists, and some of them didn't want to have anything to do with it, I can assure you. And there were similar conflicts between other centers. JPL would have loved to have had an institute based on Mars exploration, for instance. And this sort of thing could be, there are lots of permutations, but basically they wanted to join and get NASA money and get NASA blessing for their work to do what they're doing. So we've always had this balancing act between the collaborative effort and the ability to synthesize from different disciplines and a more directed effort from the top. Scott referred to that. We did not want to have somebody at the top, what was the term, Scott, for this the super biologist that was going to be in charge? King Kong, yes. We never wanted a King Kong. I mean, maybe some people did, but that wasn't the best way to attract these teams that would propose as teams with their own people and then work with us. It didn't always work, even when people wrote good proposals and were selected. There were at least 2 cases of early teams in the NAI that were top scientists, said, fine, we'll do it, we'll work on it, and then send us the money, and in 4 years, we'll send you our report. We do not want to go to meetings. We do not want to work together with other teams. I mean, maybe it could happen, but that's not the objective. So as all of you who are in the Institute or have been know, this has been a constant tension as to how much time and effort the teams are supposed to spend on collaborative and collective work, as opposed to just going off and doing their own excellent science. Well, how much time do I have left? 5 minutes. Okay. Let's just talk a little bit about the way we got the first plan, proposal. I'm not sure I like the term roadmap, because a roadmap, again, suggests to me a directed thing, whereas the way the NAI is operated is as a collective of different teams coming together, trying to find common interests, and not just from one discipline to another, but from one university or other source to another. And it works beautifully with some people and not with others, and I think that's just human nature. We try to facilitate it, but it doesn't always work. Well, what was the Institute trying to do? Carry out world-class research, multidisciplinary, to coordinate and collaborate across teams and across disciplines, and also serve NASA's needs, for instance, in providing scientific information and teamwork for missions. Dan Goldin was adamant always that this was not a ivory tower type of situation like a university, that we were not working for missions, but NASA created us because they wanted to have the best scientific talent and the best planning in the NASA missions. And we knew we were entertaining an area that simply had not been done before. You can look at all the individual elements that might go into understanding life, but it's not already existing. The exobiology program was an excellent example of a fine program, RNA program, supporting individual scientists are doing individual things. It was not based primarily on collaborations. And some scientists loved it, and it has its virtues, certainly, that you go as an individual PI and get a grant, but some bought into the collaborative effort, and especially the things that went along with it. We were trying to understand life in its broadest way, more so than exobiology in a way, because exobiology, by its name at least, is biology in space beyond Earth. Astrobiology is the basic origin and evolution and interaction of life. So it includes life on Earth. In fact, that only makes sense from a research point of view. If we want to understand the origin of life, for instance, almost the only data we have is data from life on Earth, which we then hope we can extrapolate to Mars and other places. It's very broadly based. And the first roadmap was an amazing thing. We had a couple of hundred people show up at Ames. This is before the Institute even formally existed. There were, I think, 3 Nobel laureates. We all met here and talked for 2 days. And we came up with the first elements of what astrobiology is. It was wordy, of course, but basically had to do with the origin, evolution, and distribution of life. And on the final day, I'd written down, on a whiteboard, a whole lot of stuff that was good. I said, how are we going to condense this into something that's easy to sell? And Mike Numa, who's here, yes, as I believe it was he who suggested these is far too wordy. What we really are wanting to study is, where did we come from? Are we alone? And where are we going? And I thought that was pretty good. And I wrote that up as our first view graph of the purpose of the Institute, the study of the Institute. And I, lucky me, got to go give this to Dan Goldin. And Dan Goldin, in characteristic style, interrupted me and said, no. That's far too trivial sounding. You want to write something that sounds scientific and technical. So you go off and rework those 3 things in a way that sounds like it's a technical document. So I did. And you've all seen it because on a lot of NASA things, it's about 4 times as many words to say the same things. And Dan, I took it to Dan. He said, yeah, now that sounds like a scientific thing. The funny thing was that a year or so later, when I was on a stage with Dan himself described astrobiology as, where did we come from? Are we alone? And, the same terms. It just comes naturally to what you're saying. So Dan's okay. One final point then is the education and outreach. I think one of the greatest accomplishments of the astrobiology program, and especially the Astrobiology Institute, is the development of university programs, of students who are tremendously excited and interested. We really have created a new field. And we've created a new field that's of interest not only to students, but to the public. I think more than most other things. I mean, you can't beat a good Mars mission or something like that. But on a more intellectual level, there are now many dozens of students who've gone through PhD programs created by the NAI and its members, who have become a scientific cadre of great enthusiasm and interest in astrobiology and life and the origin of life. And that may be the best heritage in the end of the Astrobiology Institute.
So now I'd like to introduce the second half of this tag team to dive deeply into Astrobiology Roadmaps. Another longtime friend and colleague, Dave DeMarais. Dave?
Thanks, Scott. Okay, well, this is a lot of material in a few minutes, so I'll just jump right in. But really, in a way, the roadmap came at a time in the late 90s when Dan Goldin, coming from the aerospace industry, said, all good businesses have a business plan and a roadmap and all of that, which really sort of charts the future and allows them to get support from various quarters to proceed. And this is very much what he brought as a mandate for doing roadmaps and decadal surveys and all kinds of things that I think have really ended up serving NASA very well. What I'd like to talk about, though, is how the initial roadmap, it sort of identified the playing field. That first roadmap in 1998, all the key elements sort of identified what it was that they had in common that could then come together to form the field of astrobiology. But what of course happened subsequent to that is, how changing mandates from headquarters and of course discoveries within the field compelled the updates of the roadmap, which now happened 3 times, as you can see by the 3 dates up there. I think this makes it go forward. I think what I'll do is just do that. Okay, so, just as it was mentioned, a lot of fields were being sort of pushed together to try to synthesize this field of astrobiology. And so very early on at the first conference and also in these revisions, it was realized that you needed an interdisciplinary team, not only just interdisciplinary in terms of science, but also in terms of where they come from, government, university, and research institutions. And the 2 revisions that I chaired in 03 and 08 definitely lived up to the spirit of that. And again, to sort of address some of the issues that were raised, we first had to agree on vocabulary. I mean, some words meaning something in one field, different in another. So just a lot of that had to be done. The revision in 2015, they brought in a professional sort of organizer who knows how to do these group think things, and was meant to be a completely independent effort from the 25-member group that was up there 2003, 2008. So there were a lot more attendees. They were supposed to just start from ground zero. I was told to shut up and sit in the corner. Don't influence them too much about the earlier roadmaps, just see what the grassroots has to say about it. And so you can see at 60 at the initial retreat, 250 people participated in webinars, all this modern technology being brought in, and then 25 at a final integration workshop. So they were sort of different in terms of the number of people and some of the electronic support stuff that was done, but they all shared this notion of drafts being presented at conferences and advisory groups and being posted on the websites for a lot of comments over a period of several months, and then the final revisions based on that. So it was very much an attempt to have an interdisciplinary or a multidisciplinary community group from a variety of institutions. So this is not just a few people sitting in a room someplace. So basically, what's interesting about this now is you're looking at the structure that we came up with for 2003 and 8, and I'm just showing the 8 one here, and then the 2015 one is sort of an indication of what it was we were sort of chartered to do, what we're trying to accomplish as the years went by. When I was assigned to do this in 2002 or so for the 2003 roadmap, I said, they told me, they said that first roadmap really defines all the elements and everything, but we don't see priority here. A roadmap, and this is just something I think either Dave or Scott alluded to earlier, is that they really wanted to have some sense of direction and prioritization. And they said, there's all this stuff in this field, what's the most important thing to do? So we had goals that were multi-decadal in scope, objectives which were supposed to be acted upon in a 3 to 5 year scope, and then each of these with example investigations. Example investigations, you obviously couldn't have this mandate of what they should be, but they did. The people proposing to this would have to justify in how their proposed work would fit into the context of the goals and objectives of the roadmap. Now, the other interesting aspect about this was we were really trying to identify common ground between astronomers, planetary scientists, and biologists. You know, what is it that they could tweak in their fields that sort of builds towards a central theme that would be this astrobiology interplay between those fields? And so you see here, as you go down through the list of goals, it's very much out in the astronomy domain of habitable environments in the universe, environments and prebiotic chemistry as might be influenced by processes out in space. And then moving down the list, how life emerges from this, origins of life basically. And then once you have a planet like Earth, how life evolves and the role of environmental change and all of that. And then of course, there was this future of life theme at that time, which was both on Earth and on other worlds, which is sort of like a space biology thing. And of course, each of these with these objectives and with example investigations. However, when the 2015 thing came along, they said, well, we don't want you to be so restrictive in priority. We really want you to get deep into all the aspects of astrobiology and make it almost like a textbook type of structure. So they actually called it a strategy. And each of these 6 major themes that were identified, you know, did have that sense of strategy in there, but mostly it was a very encyclopedia. This document's 160 pages long, the 2015. But what I'd like to point out is that when you look at the list of the themes compared to the goals, there's a lot of, they're very similar. They're just repackaged in different ways. But the one down below really emphasizes, I think, more than the previous ones, just all the advances in biology and all the dimensions and aspects that one could pursue in astrobiology, representing the ongoing maturity of biology as a 21st century science. A lot of words on one slide here. I got to get back on schedule. So to do that, we go to, I looked at all these roadmaps and with emphasis on the latest one, 6 themes that really represent sort of how the science has been partitioned into some key activities. Non-biological origins of organic compounds in space and in planetary environments. Again, you know, organic chemistry is the chemistry of the universe. You're working with the first and fourth most abundant element in existence. And so it's not that there's, you know, are there organics out there? They're everywhere. But really, what are the sources, activities, and fates of these organic compounds in space, as well as how they might be contributed to the Earth? And so this definitely is something that astronomers have stepped up to. It's a way they do astronomy is looking at organic compounds as evidence of process and conditions out there. Then how does that connect then to potential contributions of organic matter to a habitable environment? And of course here, this on the left illustrates that we have this environment on early Earth, which was the cradle for the origins of life. And so what is it that was in the environment offered up as conditions as well as ingredients that worked together in some way to create life? And of course, on the right, you can see that we're now seeing places where we're finding organic matter on other bodies. On the right, of course, with the Allen Hills thing and also the discovery by Curiosity, we are now being confronted by organic matter in other planets. You know, what is the process that caused that to form? And so we need to consider all aspects. The next thing, of course, is origin and evolution of planetary systems and habitable environments. What are the fundamental ingredients and processes in a planet that is required in order to form a habitable environment? And you can see a number of the aspects down there, including the changes in that environment over time. A test subject we would love to have is an habitable but uninhabited planet. It would be a perfect testimony to what environment's like and the kind of noise they create as a background against a signature of life that you're trying to detect, because that's ultimately a signal to noise thing. So we'd love to have that object. Maybe Mars is, we'll find out, but the point is it's an important aspect. And of course, I don't need to tell anybody in this room now with the discoveries by Kepler and radial velocity techniques that we've got a lot of, N has gotten to be a very large number in terms of planets. And now it appears maybe a pretty good number in terms of habitable planets. As you see here, plotted mass of the parent star on the vertical axis and distance from that star on the bottom. This is just sort of a model based on Earth. That's something Jim Casting and co-authors did some time ago. But it shows now that we've got candidates that you can use to fill this diagram in various directions. And so we really now have a lot of test subjects out there to explore this notion of habitability on other planets. Origins of life, obviously, synthesis and function of macromolecules and the origin of life. I'll just quickly say that the macromolecules that have biological function are sort of one of the keystones of what life is about. But the big challenge is, how do they play nice together? How do you go from just interesting molecules, macromolecules, to systems, networks of reactions that ultimately emerge to create this thing that we call life? And it's that interaction between them that still is a big challenge. But of course, biochemistry and molecular biology are making enormous strides. And, you know, we've got a lot of reasons to be optimistic about progress on this one. And again, knowledge of that prebiotic environment, together with understanding how macromolecular subsystems come together to form what we would call a protocell, that's really sits at the core of trying to define, and I should say, origins of life, because life could probably begin in different ways, perhaps, for all we know. And that just underscores the importance of, well, stochastic processes, but also the role of early planetary environments. Living record, once life starts, how do you go from origins of life to sort of more towards increasing complexity? There's a theoretical approach to it, as well as you know, molecular laboratory experiments and observations of life. And again, another field that's just absolutely expanding dramatically, and a lot of details indicated here. Just moving along. And of course, we have the living record of life and its early evolution. Of course, the famous ribosomal RNA tree, but now we're coming up with trees of other types of proteins and so forth that are really important in life, and putting all this together to really try to do a reconstruction of what early life is like. And in the lower right, just sort of a micrograph showing a microbial ecosystem. There's literally thousands of different organisms in there interacting with each other in ways that we don't understand. But that's the crucible in which evolution has occurred, and our ability to drill into these systems and really understand the microenvironment that shapes the physiology of the organisms is really just as important as doing the genetic stuff. Geologic record is the parallel record to that. It's what we see preserved in rocks. How has life interacted with the environment to create the trajectory of life that we've seen? And then, of course, the role of extraterrestrial events and all of that as well. So this is sort of the geologic side, with obvious extensions to Mars. Here's sort of a clock that illustrates, you know, time is sort of on the dial of a clock face from the origin of the Earth going around. And just to remind us that a lot of things happen over that long period of time. You can see some examples of that at the bottom. Most of life has been microbial, which of course is a huge clue that that's the kind of stuff that we should be sure to look for on other planets, and therefore give us clues as to what types of features we might look for. And then finally, signatures of habitable environments on life in the solar system and beyond. You know, how do we actually go out and observe features that can tell us about what the early environments were like, or what the environments are like now, and what are the signatures of life, so-called biosignatures. So characterizing habitability at different spatial scales, from what you could see as a single pixel off afar, all the way down to the kind of details of a microbial ecosystem that really determine its success. And then again, just really expanding the study of signatures of life in different flavors and types, and as appropriate for the type of venue you're trying to explore. And of course, as it says here, we're not just trying to characterize evidence of life, but evidence of what environments were like. And of course, there's the list of different types of categories of biosignatures, from organic matters and minerals to structures and other types of chemistry and isotopes. If you're looking for extant life, you're looking for activity. That was what Viking was centered on. But really, I think certainly what we've learned from early Earth is that you need to engage all of these. And this is really important for mission design, because each of these types of features appeals to a type of measurement that should be made and should be debated as to whether it's worth making. And I think that drives a lot of instrument design now that's going into planetary missions, and for that matter, astronomy. And so in the case of astronomy, you know, you have to, whatever feature, whatever signal you're getting off of a distant planet is either coming from the surface of the atmosphere, but in any case, you got to run the gauntlet of the atmosphere to get out and to be detected. And so this is this whole new science aspect of astrobiology now that's really centered on the exciting advances that have come from, you know, Kepler and other missions. And so it's not just science and so forth, but there's philosophy and principles that are involved. Astrobiology, the roadmaps have also been importantly pointing out those types of things. As been said many times, it's multidisciplinary in its content, but critically interdisciplinary in its execution. A very central point of astrobiology. Planetary stewardship is encouraged through emphasis on protection against forward and back biological contamination and recognition of ethics associated with exploration. The broad societal interest, stake, and participation in astrobiology is really crucial for nothing else but for support, but also for just enlightenment of all of us. And then, of course, public interest, and this is a point Dave Morrison finished on, creates an opportunity and a mandate to educate and inspire the next generation, and thus astrobiology should include strong elements of education and public outreach. In the last astrobiology and strategy thing, we even got into this whole notion of humanities and social sciences, and there's a whole subgroup there involved that got into epistemology, social science, ethics, history, law, communications, education, and frankly, a lot of things I hadn't really thought about. But yeah, you know, I mean, if there's this much importance to it and significance for the public, these are all very important aspects that should really be folded into our consideration going forward. This is what in many ways matters to most people. So just to finish, you know, astrobiology really does unite disciplines to study evidence of life in the universe, from the astronomical domain, the molecular biological domain, from planetary evolution and so forth, all being brought together to understand origins, evolution, and distribution of life. This is what excites kids. It excites the future because they see the problems of the world. They see evidence of the climate change and all this, and they know that the science of the future is interdisciplinary science. And astrobiology is just an incredibly inspiring way to get them engaged to move forward. Thank you.
Now I'd like to invite Lynn Harper to come up and share her thoughts about some of the early days and why in the world would Nobel Prize winners be interested in this field. Lynn?
What's that? Laser pointer here. Which one? Top one? No, the white one. The white one. Yeah. And then you just do the computer to do this. Okay. If I mess up, come get me. Okay. Well, good morning and happy anniversary to the NASA Astrobiology Institute. May you evolve to be something even greater than what we first started. So my name is Lynn Harper, and I'm lead of integrative studies for the Space Portal now, but I am the initiating founder of the Science of Astrobiology. And in consideration of full disclosure, I will let you know that Dave Kooris is my direct supervisor. So now that he's left, I'll tell you exactly what happened. And that is that Dan Goldin hit NASA like a comet. He disrupted the local ecology at headquarters, and that spread out to the center like a nuclear winter. Except it was a very positive nuclear winter in that he questioned absolutely everything that was fundamental about what NASA was doing. And also what was going on at the time was base closures. It was the thing to do. The BRAC Commission was formed and people were looking at closing bases. And one of the bases that NASA was looking at closing was Ames. They felt that Ames was way too diffuse. That we were doing aeronautics, we were doing, information systems, we did exobiology, we did space sciences, we did earth sciences, we did life sciences. It was just a mess. And Ames, by the way, at that time was trying to convince everybody that this was a feature, not a bug. And it was falling on deaf ears. So there was a red team white paper that was circulated. No names were on it. And basically it laid out the plan that space sciences at Ames would be sent to JPL. Earth sciences at Ames would be sent to Goddard. Life sciences at Ames would be sent to Johnson Space Center to merge with their human research program, and then everybody would have their nice specialty areas in neat boxes. I got the call, I got an email from the org director at the time that was Bill Berry, and at that time, Bill Berry was acting org director. Before that, he had been division chief of advanced life support, and I was his deputy. I was now acting chief of advanced life support. And so Bill says, we need a going out of business plan because the associate administrators of all of the NASA major organizations and France Cordova, the chief scientist, would be at Ames on the following Sunday. This is a Wednesday. On the following Sunday, to hear our plans to transfer Ames to either an institute or to the UC system, split up all of these programs and have and disperse the people. And I called up Bill as soon as I got the email, and I said, you can't do this. This is the only place in the world where all of the intellectual horsepower comes together to understand the fundamental nature of life in the universe in all of its aspects, from its cosmic origins to the origin of life on this world and others, to whether or not we're alone in the universe, and what happens when life from one world leaves its planet of origin and goes elsewhere. I said, it's all right here for the first time in history. You cannot let this go. So Bill Berry said, give me a better idea. And I said, when do you need this? He said, tomorrow. Tomorrow. So I had the privilege of participating in all of those workshops that John Rummel was showing that were foundational to both the exobiology program, Search for Extraterrestrial Intelligence, the ECHO report, and Understanding Living Worlds. And I drew from that the eloquence, without his eloquence, unfortunately, of John Billingham, who talked about how an infinitesimal amount of the matter of the universe was concentrated in the human brain. And from that, we can understand everything from the beginning of the universe itself to and to create destinies that extend beyond it. And so I packaged all of that together, drew on the wisdom of people like Dave Peterson and Estelle Condon in Earth Sciences, of Joan Vernikos, Malcolm Cohen, and Mella Werner in Life Sciences, Don DiVincenzi, John Billingham, Chuck Klein from the Space Sciences area, and walked into Bill's office at 8:30 the next morning with a program called Life in the Universe. And Bill says, this is not what they're asking for. And I said, what are they going to do? Cancel your programs? We had nothing to lose. Bill assembled the scientists at the time, and during this time, we were doing some background work on what were the grand challenges in each one of the disciplines at Ames. And then we asked the question of what would happen if you took those grand challenges, you took all of our capabilities and merged them. What could you do that you couldn't do in the separate areas? And the result at that time was staggering. The report is floating around somewhere in one of my boxes in some back room, but I'd like to drag it out because I think it's as relevant today as it was then. At any rate, Bill brought the scientists together. Everybody agreed that this was a better idea than basically going out of business and canceling all the programs and dispersing it. And on that Sunday, where Wes Huntress was there, Bill Berry presented the concept of life in the universe. And Wes said, I really like this idea, but I don't like the term life in the universe. I think we should call it astrobiology, and astrobiology was born. Now, how many people in here are parents? Okay, so you know that being born, bringing the baby home from the hospital, that was the easy part. You have to raise the child. And so we started the Astrobiology Advanced Missions and Technologies. I was its first lead. And as we just started to get rolling, I became pregnant with twins. And during that pregnancy process, we developed most of the 10As of astrobiology. Jerry Soffin came in from Goddard to help out, and we got 100K of resources to spend as we wanted. So what we did is we spent it on Kepler. We spent it on the Chem instrument for the Mars missions with Carol Stoker. We supported Dave Blake in the Chem instrument, and we supported Stoker and Lemke in the Mars missions, all of which resulted in successful experiments. So I always thought this is a wonderful slide representative of astrobiology, because it basically says there's a whole lot out there that we haven't come near to understanding and exploring, and that's part of the future. I did want to talk to you about the past and the early days, but also what's ahead. So why did 2 Nobel laureates chair sessions at the first Astrobiology Roadmap workshop? Before I start the Astrobiology Roadmap workshop, I want to say some names that you probably haven't heard. Some of you have never heard them, but all of you who were there for the first days of astrobiology may remember. Kathleen Canal. Kathleen Canal was our political and operative and our PAO person, and she had a network that spread through every state and Congress and the Senate. And she was absolutely essential in providing the advocacy and support base that we needed for the development of astrobiology. Geyser. Karen Geyser was one of the people that worked with Greg Schmidt to have a successful first astrobiology mission. Because I'll tell you the story, right after we started astrobiology, headquarters said we could not fly any astrobiology missions. Other people could fly astrobiology missions, but we couldn't fly astrobiology missions. So this was the time where everybody was splitting things up. This was focus. Focus was the key word. We need to focus. We need to, get those stovepipes really shiny. And I said, we're NASA, we have to fly things. And most of the things we need for astrobiology are in some other world, are out in space. So we snuck it in, our nose under the tent, thanks to Harry McDonald at the time, which was the Leonid meteor storm. And right before, when we started working on the Leonid meteor storm, this young professional comes into my office by the name of Greg Schmidt, and he says, I'm very interested in astrobiology. He says, is there something that I can do? Now, by this time, my twins were 3 months old, and we had not slept in 3 months. And I looked at him, and I go, well, what's your background? And he said, well, I was the project manager for the frog embryology unit on the space shuttle. And for those of you who know, that rewrote the embryology textbooks and the general purpose workstation, which was also one of the most difficult and fundamentally important tools that was used on the space shuttle. He says, also, I built an observatory and ground the lens for the telescopes when I was 16. I go, whoa, 16, not old. Whew. And I said, I have an idea. I said, why don't you come in as co-lead for astrobiology advanced missions and technologies? And Greg said, is there such a thing? And I looked him right in the eye and I said, absolutely. So where does all this go and how do we get there? What Greg and I did, and with all of the people that, many of whom are in this room, is that we started to re-baseline where we were in the nature of life in the universe. What new things do we know about the origin of life? What things new do we know about the distribution of life in the universe? What tools do we have today that we didn't have then? And we started creating workshops. We did 9 of them in 1 year, where we brought in, but we did a little bit differently. We didn't just bring in the scientists. We brought in the scientists, the technology developers, and the mission developers all at the same time. And because we needed the tools, and we needed to baseline what were the tools that we had going forward, as well as the questions. Because what was just beginning to look like is not that we were necessarily posing new questions, but that we could answer them. And that was galvanizing. So we had 9 workshops. They were all multidisciplinary. And I remember the great Mars scientist, Mike Carr, coming in and saying, this is the first workshop I've gone to that I don't know everybody in the room. And that to me was one of the great themes in astrobiology, to create a nurturing place where people from multiple disciplines could come together, share their knowledge, share their tools, and then go do something else that's extraordinary that they wouldn't have done alone, wouldn't have thought of alone. And that's what brought in the Nobel Prize winners, was the multidisciplinary science. So why? At the time we were doing this, there was a group that we started calling Evo Devo. It sounds a little bit like a metal band, but what they were evolutionary biologists and developmental biologists. The evolutionary biologists wanted to study the origin evolution of life on Earth, and the developmental biologists wanted to connect the first cell that in the egg and the union of the egg and the sperm through the development and embryonic development of a human being. And what they noticed was that ontogeny recapitulates phylogeny, which means that the human body goes through all of the steps of developmental biology during the course of pregnancy. This is something that was, of course, you know, in the forefront of my mind at the time. And they could not get any funding because they wanted to work together. The developmental biologists felt that the evolutionary biologists had insights from evolution that could apply to a better understanding and a better protection of the developing fetus. The evolutionary biologists noticed that the developing fetus went through the major steps of the evolution to a human being. They felt they could get insights in evolution by studying developmental biology. So they proposed to both NIH and NSF. NIH rejected their proposal because it had too much evolutionary biology. NSF rejected their proposal because it had too much developmental biology. We were one of the groups that supported these groups and the research that they had done. Okay, so when at the first roadmap workshop, I asked Bruce Bloomberg why he came. And he said it was because of the multidisciplinary science. He felt that everything had become so constrained that it was no longer possible to make all of the discoveries that we needed or we wanted. So what got Nobel laureate Bruce Bloomberg interested in leading the Astrobiology Institute? It was a study by Tim Hammond, who was the director of transplant surgery at Tulane University, who had no interest whatsoever in space, but what he was interested in is getting a better kidney cell culture to save lives. So what this is the first time that DNA was applied to a space life sciences investigation aboard the space shuttle. And right here, you're going to see the image on the left is the first Affymetrix chip, 10,000 genes. And what you're going to see is how it changes. Oops. Oh, no. Oh, there we go. Okay. So it changes as a result of the mechanical culture conditions. So in the second thing, you're seeing a rotating wall vessel, which emulates microgravity. Tim thought if he could use that, it might get better results, and it did. But what really happened, what got Barry interested was this one, because that's what happened when we sent it in space. Of the 10,000 genes studied, 1,600 changed in a pattern that had never been seen before, but actually the stress proteins were lowered. I contacted Barry and asked him whether or not he would review this. He got very excited about it. Shortly thereafter, I was in Dave Morrison's office with Greg Schmidt, and we were talking about who would be candidates for the director of the Astrobiology Institute. And Barry was so jazzed about this particular piece of research that he organized the Stanford University molecular biology group to come down and review it. And we got to talking some more. And I said, you know, I know somebody that might be interested in doing this job. And I said, it's Barry Bloomberg, the Nobel Prize winner that was at our workshop. And so Dave brought this up to Scott and to Harry McDonald, and the response was positive. So I called Barry and I said, Barry, I think my management is going to offer you a job and I think you should take it. And Barry said, why? And so we go, well, I can't say exactly what it is, but you'll have access to spaceships. And he started laughing. He goes, all right, now I'm intrigued. And those of you who know Barry, you know that was like candy to him, to be able to access other worlds and other ideas. All right, so the future. What's in your toolkit? How many people in here have had their DNA done? All right, that was not even a possibility or a glimmer when we started astrobiology. So you've got tools from 20 years of technological revolutions. You've got AI. You've got super miniaturization. We saw the beginning of it when we were doing the first Astrobiology Roadmap workshops, where people were pulling flight instruments out of their pockets. We never saw anything that small or that diverse at the time. And all of these tools amplify the value of all of your flight missions. But in addition to that, what's happening in the revolution of COTS and commercial space is that you're going to be getting much cheaper flights coming in over the next decades. So, astrobiology, life in the universe, where you can find it. So one of the things to do is find it. I thought we would have found it by now. after 20 years, I really did think that we would have found it by now. So this is still on our to-do list. And also we need to find those biological connections from the Big Bang to the big brain. So this is astrobiology, life in the universe, where you can find it, and then where you can take it. We have 20 years of existence proof of people living beyond Earth. We're planning to develop, to go to the moon and to return people to the moon in a sustained manner. This is the story of the first generation of the only life in the universe we know, in our first generations beyond the planet of origin, informed by all of the tools of contemporary society today, contemporary high tech, which is growing by leaps and bounds. And there's very different futures that are available to species that can thrive beyond their planet of origin versus those whose destinies are constrained to a single world. And I want to leave you with one last astrobiology thought. As we go and access other worlds with life, with ourselves, with people, with animals, with plants, as we build habitats and housing on other worlds, two extraordinary things can happen. Either when we go there, we will encounter alien life, and the question of whether or not we're alone, at least from a microbial perspective, will be answered conclusively. But if not, we are the origin of life on that world, with all of the evolutionary potential that that offers. And so I wish you another 20 years, go make discoveries, and I hope that as the years go on, I will see bigger and better things from the NASA Astrobiology Institute, because it's already been an extraordinary ride. Thank you so much.
Wow, that 25 years ago, I thought that Lynn Harper could sell ice to Eskimos, and she doesn't let me down at all. What an amazing ability to communicate. All right, so now we're going to turn to the early years of the Astrobiology Institute, particularly those that involve Barry Bloomberg, and for that, another longtime friend and colleague, Rose Grimes. Good to see you, Rose. Floor is yours.
Thank you. Thanks for that introduction and for the invitation to speak today. I also have no PowerPoint slides for you. I thank Dave for warming us up for putting on our listening ears without having visuals. Having just retired from NASA after about 30 years at the end of August, I now live in a PowerPoint-free zone, and I try to keep it that way. So I've been asked to talk to you about the early years of the NAI. We're turning to the cradle of the organization that we're here to celebrate today. We've heard about the deep planning and the extensive road mapping, and the support from Ames and from some of the enlightened at headquarters, and the enthusiasm of the scientific community. Scott and others worked with genuine creativity, surfing the wave, a very dangerous wave, and hoping not to face plant, and hoping not to get caught before they were able to succeed. Then they handed on the baton to mix metaphors in this high-stakes relay race. NAI's initial years and early accomplishments are the result of the commitment and engagement of so many people. I would use up all of my time if I were trying to list them. We've heard some of their names, but I want to call out generally, although with heartfelt gratitude specifically, some primary groups of people. There was the team at NAI Central. That was what we called the NASA management here at Ames for the Virtual Institute. There were the funders and the advocates at NASA headquarters, the principal investigators of the Institute's teams, whom taken together we called the Executive Council, and all the investigators and student researchers who participated in the Institute. Because all these people suspended disbelief, they suspended cynicism, and they were willing to embark on something genuinely radically new, to put an architecture in place that could carry forward all of these great ideas about road mapping and interdisciplinarity and create something. They put their energy and their belief into it. And what they were focused on was something so revolutionary, it was unprecedented. And that's really the key to what I want to leave you with today, the concept of unprecedented and precedent. It's the difference between thoughtful creativity and creative reality. It's an important distinction from the adjective groundbreaking, which has also been applied to the Institute very appropriately. We were groundbreaking, but we wanted to build on top of that broken ground. We were committed to the Institute as a cornerstone, as an anchor to what we've heard so much about this morning, the field of astrobiology. The team at NAI Central pretty quickly came to understand that they were building a foundation. Setting precedent and following precedent was key to a self-sustaining institute culture that all the participants could count on, could reliably interact with, could identify, understand, and choose to belong to. A culture supported by an architecture to instantiate all the road mapping and the virtual institute dreams. At the outset, for sure, we made decisions as they needed to be made based on the information available, which was rarely the best information or complete information. We were innovative and reactive and responsive. We very quickly discovered, though, that having made a decision and put it in the book, so to speak, we quickly discovered that resolving one question led to dozens of additional questioners who all wanted the same attention and the same resolution. People wanted and expected consistency, fairness, transparency from governing structures, particularly those managed by federal employees with tax dollars. Imagine. Many of the challenges that established precedents for the NAI and produced the culture can be seen in light of the milestones of the cooperative agreement notices, and that's how I'm going to orient things. All the applicants to the first opportunity believed they would be selected. But of course, a competition results in awards and thank you for your interest letters. In the aftermath of the first awards announcement, we quickly realized that the dynamism surrounding astrobiology, not only nationally but globally, was focused on the NAI and on membership in the NAI. Many researchers were not going to be among the first awardees. And many research teams in the international community wanted the recognition and the validation and the collaborative benefits that association with the NAI could bring them. Grappling with the Institute's responsibility towards that larger community led to innovations like the NAI's Focus Group Program and the International Partners Program, just to mention two of many. Each of those, again, to be transparent and equitable, needed to have structures to accommodate the functions they needed to provide and to be understandable to potential participants. They were among our first lessons in our obligation to create solutions with longevity, precedents, and what building for longevity meant. We never stopped struggling with questions of using NAI resources to support member functions and desires and using those resources to address the community's advances. Because we needed to say, not it. With frequency, we knew we needed a consistent and articulated rationale behind every answer, especially behind every answer that was no. And those were all precedents. At the time of the second cooperative agreement selection, we were adding to the first group of teams, which still had another 2 years on their 5-year awards. And my reflection on that experience centers on the trip I made to NASA headquarters to brief the selecting official responsible for making the final determination. Before the astrobiology program executive, Mike Meyer, and I could even begin, the AA announced in no uncertain terms that if we were going to propose the usual suspects, we could just turn around and go back to the drawing board. And I was really unprepared for that. I thought Mike and I were prepared for anything, but I wasn't prepared for that. I didn't have a usual suspects mentality. We'd done a lot of innovating in the previous 3 years, started quite a few projects and programs, and all of them were based on internal and external consultation with some form of competition and non-advocate review. So that was our precedent. The approach Mike and I recommended for the second selection was based strictly on the independent science review. We had considered other options, but those were driven by the budget available, which didn't really allow us to select all the teams we wanted out of the top rank of the science review. But every way we looked at it, we just couldn't see a better solution than simply going with those review scores. And in the end, that's what we proposed. And we decided to creatively negotiate and ask for more funds in order to fit them all into our selection. But that set another precedent for the Institute. Scientific excellence, independent from other considerations, was a reputation that we wanted to espouse and to maintain. Between Can 2 and Can 3, in several different teams, multiple Institute investigators who often had published really different interpretations of the history of early biological life on Earth found themselves at odds over an issue involving NAI-sponsored fieldwork. And it wasn't hard to become aware of this. Tempers were high and words were exchanged. Folks felt much, maybe too much, of their planning for future field research had been shared openly at internal Institute meetings, and as a result, some felt that they'd been disadvantaged by that openness, although encouraged to do it, to be open by the NAI. And this was a turning point for Institute management. I was at the time acting director, and Bruce Reniger was the anticipated incoming director. And we knew that this was an important controversy. We were able to act as brokers based on the precedent that we as an organization and we both individually had developed. The various parties agreed to meet together. It was either an AGU or a GSA meeting. I know it was in Denver. And these discussions were very frank, very open, and very uncomfortable. In the end, the participants mutually agreed on an outcome, and this led to the astrobiology drilling program. They agreed to pool resources on the field site work, lowering costs. They agreed to share the resulting samples, and we agreed, the NAI, to curate, archive, and distribute the samples to the wider scientific community through joint support of the NAI and the National Science Foundation, which was another precedent-setting cooperation. And that whole episode was a chance to think big. And it wasn't the last time that the NAI would wade into a scientific controversy, alone or with partners, to offer a seed crystal for a solution. The third cooperative agreement round was also precedent-setting. It would be the first time we put our foundational concept of open collaboration within and between teams up against our principle of competitive selection for scientific excellence. We would compete newly available slots for prestigious participation in the Institute, and predictably, we would see existing teams go head-to-head in that competition. After having collaborated and shared expertise, ideas, capabilities, and as we've seen, sometimes proprietary concepts for 4 years. Could we do that without harming either the collaborative or competitive principles? We were also opening up once again to new participants. And our precedent promised there was no legacy advantage. Could that be true? Would the community believe it? As well-intended as multiple reviews that we'd undergone by many external and internal boards, this really was the event that would prove and sustain the Institute or reveal the intrinsic weakness in the idea. You won't be in much suspense over this, of course, as we're here to celebrate many more years of the NAI's impact and success, but bear with me and pretend it's a teaser. So the preparation for the fourth cooperative agreement selection was one of my last activities with the Institute. And what stays with me from that experience, I feel is really extraordinary. There was a budget reduction we needed to manage, surprise, surprise, which would delay the fourth selection opportunity and, of course, the resulting awards from that fourth selection. The teams that were selected in round 2 were due to complete their terms before the potential for proposing, if they chose to do so, to have the option to propose into the fourth selection. And of course, competition doesn't guarantee selection. So as the impact of this became recognized throughout the Institute, the principal investigators from round 3 proactively consulted with each other and proposed to NAI Central and to NASA headquarters their wish to voluntarily take proportional budget cuts to their ongoing budgets in order to return the funds to the Institute and enable their distribution to their sister teams, even if only on a shoestring basis, until the next selection opportunity could be realized. And I think that really says something. As we know, scientists don't voluntarily ask to take less money. But after a period of almost 10 years of precedent in the Institute and a number of years for these CAN 3 teams working together and working with their collaborating teams, they recognized the value of the structure. They were voting with their budgets for the Institute's collaborative and inclusive and diverse nature, and recognizing the value to the NAI as a whole of the participation of those colleagues. They were voting for self-interest because they had important ongoing activities with those teams. And I believe they were voting for their belief in the competition results because they were going to welcome the next teams, whoever they were. So I feel like that was an indication they were voting for the NAI. And so to wrap up that hanging chat I left you with from my lesson about the third round selection, that's it, because all of those PIs making that offer were teams selected in round 3. So I think that was a great result. And then one other thought that I wanted to share with you came to me when I was considering my personal experience with the Institute. During Barry's tenure, a lot of the team at NAI Central, not all, but a lot, were women. And someone once mentioned to Barry, or congratulated him on the activities, and this individual credited them as being Barry's girls, which took his fancy. And so after that, Barry used to often refer to us as Barry's girls. Honestly, I struggled with that description, particularly as an emphasis, a thread in my own career has been in advocating for equal recognition of women in science. So the experience reminded me to keep working on gender equality, and particularly to use the agency of the Institute when I could. So when NAI supported scientific meetings, one of my requirements was that there be equal representation of women among the speakers and panelists. When Jill Tarter and I proposed a panel to a AAAS meeting, and we were asked why the panelists were all women, we asked them to clarify their concern. On the other hand, I was one of 4, I think, organizers of the second Pale Blue Dot meeting, which NAI co-sponsored with Chicago's Adler Planetarium. And we simply declined to address the question of how it happened that all 4 organizers were women. At that time, and maybe still, there were too many meetings where no organizers were women, and that aspect too often doesn't raise comment. It was some time and too long before a woman was recognized as an appropriate director of the NAI. But it did happen. Precedent evolves slowly. And so I end with the concept of precedent. Creating something new is laborious. It takes time. It takes consistency. It takes a village. NAI was very fortunate to have so many permissive factors come into play at the right time. It's a story we should celebrate, we should remember, and we should occasionally tell each other because it had a wealth of glorious lessons. Thank you. Cold hands. I'm glad I remembered this is the coldest meeting.
Very well done. I think one of the CAN meetings that Rose just described was when the shift had occurred from Wes Huntress to Ed Weiler. And in Weiler world, it was known that he was an astronomer. And so one of the first things I think you got blasted with is, where's the astro in astrobiology? And of course that led to some different selections. So here we have the last speaker of the morning session here, Carl Pilcher, one of the former directors of the Astrobiology Institute. So take it away, Carl.
Hi, everybody. When I saw the agenda of the forum last week, I was struck by the great job the organizers had done in assembling the people who played seminal roles in the formation of the astrobiology program, from Dan Goldin on down, and in the successes that the astrobiology program has had over the last 20 years. As we're gathered now to celebrate those successes and to look forward to the next 20 years, I'm really grateful for having a few minutes to share some thoughts with you. One of the things that I think has been central to the success of astrobiology has been the creation of the amazing astrobiology community, of which we're all a part. And central to the creation of that community, I believe, has been the NAI. NAI was enabled to be a community builder by a charter that encompassed the breadth of astrobiology, that embraced all the areas of science, training, flight missions, technology, and communication that really are essential to the field. NAI was chartered to be a focal point for representing the entirety of astrobiology, and in that I think it was very successful, and I hope that you would agree with me. Having an organization like that at the outset was very important for a lot of reasons. One of the reasons is that there were doubters. In the early years, people who followed Dan at the highest levels of NASA, and even some people in the science community, questioned whether astrobiology was a viable field. I think that's one of the reasons Dan wanted an eminent biologist to be the founding director of NAI. And of course, we're all very fortunate that he found Barry Bloomberg and persuaded him to take the job. Looking forward, the RCNs bring new strengths to community building, and I expect many successes to emerge in the future from the RCN structure. Certainly, if the success of Nexus is any indication, and I'm sure it is, we have a lot of good things to look forward to. But at the same time, I think we need to pay attention to some of the things that are in danger of being at least de-emphasized and at worst lost with the transition away from NAI. At the top of that list for me is focused support for students and early career investigators. And I say focused support because NAI brought together many different dimensions of student and early career support to provide the nurturing environment and opportunities for advancement that have led to the vitality of the astrobiology community that we see at AbSciCon and elsewhere. And just for example, the Lewis and Clark Fund for Field Research and Exploration in Astrobiology has been a very important vehicle, and this was done in collaboration with the American Philosophical Society. This has been a very important vehicle for enabling students and early career investigators to get out into the field investigating problems of their own choosing with support, both financial and logistical in some cases, from NASA through the NAI. But there have also been less visible programs that NAI has had to support students in this way. One of them is the Early Career Collaboration Awards, which provided modest awards of a few K each to enable students to travel to different laboratories where they could get mentoring from different mentors, learn new skills, and also contribute to integrating research across different laboratories. Beyond that, NAI had other ways of supporting students. For example, the NAI Director's Discretionary Fund for many years gave emphasis and priority to projects that would particularly nurture and support early career investigators. NAI also supported the Astrobiology Graduate Student Conference, which, as I'm sure you all know, is a conference organized by and for early career investigators and graduate students. And that conference, along with summer and winter schools that NAI also supported, have been cited by many early career investigators as really being life-changing experiences. All of these areas of support and the opportunities that NAI provided to early career investigators made all the difference in the world to so many of them and have led to their commitment and enthusiasm for pursuing careers in astrobiology. An example of something that emerged from all of this support, from which I have personally benefited, is the Blue Marble Space Organization, and particularly the Blue Marble Space Institute of Science, with which I affiliated after I retired from NASA. This is an organization that was founded by two entrepreneuring early career astrobiologists who are now mid-career, Jacob Misra and Sanjoy Som. And this is an organization now that is supporting many other early career astrobiologists and educating some of the next generation through their Young Scientist program. So this is just an example of what can be achieved when we provide a broad spectrum of support to early career investigators. And I hope that that kind of support will continue going forward. And I just urge you to think about that as you consider the next 20 years of astrobiology. Another area that NAI has supported since its inception, or since shortly after its inception, is support for faculty and students at minority serving institutions. This has been very important. There have been notable successes, but there have also been great challenges in that aspect of outreach. We truly need to broaden the astrobiology community and maintain a breadth across people from all backgrounds. And I hope as well that you'll give some thought to how we can continue to strive toward those goals as we go forward. Well, those are the thoughts I really wanted to share with you today. I appreciate the opportunity to do so. I'm sorry that I can't be there with you. I know I have a lot of friends in the room. It would be great to see you all again. I hope there'll be another opportunity. So Godspeed and take care.
Final words. Thanks to Carl for giving us those final words, and we'll pass on the applause to him. So now we're going to take a 15-minute break. We will reconvene at 11 o'clock, and I'll tell you all what I used to tell my staff when I was director of Ames: proceed until apprehended.